All right, hi everyone. Welcome to Zoom for Thought, first lecture of this quarter. We are planning to have 5 lectures this quarter. We may do more, we shall see. Kicking us off this quarter, we have Sam Spiro, and he's going to tell us about spectral graph theory. Go ahead.
Yeah, and I'll also note that this talk will probably be a bit on the shorter side, so do stop me at any point if you have questions or whatever.
Sweet.
But yeah, so what the heck is spectral graph theory? So it's roughly speaking the interplay between linear algebra and graphs. So one of the canonical objects in the study is the adjacency matrix, which some of you may be familiar with, but just in case, I'll redefine things. So this is given a graph G, we define an adjacency matrix AG, or just A when G is understood, to be a square matrix whose rows and columns are indexed by the vertex set of our graph G, and we'll make the UV entry of our matrix A equal to 1 if UV is an edge in G, and AUV will be 0 otherwise. So as a simple example, if we look at this graph here, vertex 1 is adjacent to 2, 3, 4, and 5. So in entries 1, 2, and 1, 3, and 1, 4, and 1, 5, we put 1s. Similarly, down here we put 1s, and there's no other edges, so we put 0s everywhere else. Right? And really, this matrix here is just a convenient way to like write down what this graph is and to like maybe input into a computer or something. The fact that it's also a linear operator a priori shouldn't really matter. Like the fact that we can multiply this with itself shouldn't mean anything. But it turns out, shockingly, that it does. And that's really what spectral graph theory is all about, is really exploiting the linear algebraic properties of this matrix and using it to say combinatorial facts about our original graph. And in particular, I'll note that the adjacency matrix is going to be a real symmetric matrix. In particular, it has real eigenvalues, which I'll order like this and denote as follows. So as a first hint of what the heck this matrix can tell us about our graph, I'm talking about walks in a graph, which is formally defined like this, but I'll just define it by example. So an example of a graph or a walk in this graph is the following sequence of vertices. 1, 2, 3, 2, 3, 4, 1, 4, 3, 2, 1. Right, so it's just a sequence of vertices, which you can get to by sequentially going along some edges. And we'll say that this walk is closed if we end where we started. Okay. And a basic observation is that the number of walks of length k from some vertex u to a vertex v is exactly the UVth entry of the kth power of the adjacency matrix. And this is just high definition of matrix multiplication. Literally, for any square matrix, the UV entry of its kth power is this sum here, where these wi's just range over all possible vertices in this case. And each of these terms is either going to be 1 or 0. And it'll be 1 precisely when the edge uw1 exists, w1, w2 exists, and so on and so forth. And this is just defining what it means for a walk if you look at the formal definition of it here. So the number of 1 terms here is exactly the number of walks of length k from a vertex u to a vertex v. This is just a basic combinatorial fact that can be represented in this linear algebraic way. And I really want to talk about results using eigenvalues of our matrix. And one result I can make there is that the number of closed walks of a length k is equal to the trace of the matrix raised to the k power. And that's because closed walks are just the walks that start from u and end at u. So in other words, it's going to be all the diagonal terms of this thing here. And the trace is literally the sum of the diagonal terms. But the trace also can be represented in a spectral way. Namely, it's the sum of all the eigenvalues of this matrix, and the eigenvalues of this matrix is the eigenvalues of the adjacency matrix raised to the k power. Right, so it's all basic kind of spectral graph theory stuff. And now we can kind of say some mildly interesting statements. So for example, I claim that a corollary of this is that if you look at the eigenvalues squared of the adjacency matrix and sum them up, you get exactly twice the number of edges in our graph. So in particular, the eigenvalues of your graph tell you exactly how many edges your graph has. And the observation to prove this is just that the number of closed walks of length 2 is exactly twice the number of edges, because for each edge, a closed walk is go along it and then go back, or start at the other end and go forward and then go back. And it's not too hard to check that these are exactly the closed walks of length 2. So you just go forward along an edge and then go back along the same edge, because we're only talking about simple graphs here. And another result, which I won't formally prove, is that a graph G is going to be bipartite if and only if its spectrum, its multi-set of eigenvalues, is symmetric about 0. Roughly speaking, this proof is if this happens, then that's equivalent to saying that these sums for odd k are all going to be 0, which says that the graph G has no closed walks of odd length. And perhaps to formulate this formally, if we look at k equals 1, if this spectrum is symmetric about 0 and we take just the sum of literally all the eigenvalues, then for every mu, I also have a negative mu. So when I take the sum over this for k equals 1, I will get 0.
Sam, you said multi-set of eigenvalues. Does that mean you're counting the multiplicity?
Yes. So
okay,
for example,
symmetric with also multiplicity, because you could have like 7,000 minus ones or something.
Exactly.
Okay,
Yes.
cool.
So to be concrete with that, if sigma of A could be, for example, the multi-set -7, -7, 7, 7.
Amazing.
And that's what I mean by symmetric about 0.
Makes
Good question. Yeah. Any other questions at this point? Okay, cool. So just to close off that thought with closed walks, if we're symmetric about 0, these sums are all going to be 0. So we have no closed walks of odd length, which in particular means we have no odd cycles. And that's one of the equivalent formulations of a bipartite graph, is that it has no odd cycles. That's essentially one of the directions to improve the other one without. So these are some moderate results. Another result that's more complicated to prove, and I will do so here, are some bounds on the chromatic number of a graph G. This is a NP hard thing to compute in general, what the heck this thing is. But you can get some relatively nice bounds using the spectral information, which is computationally much easier to compute. In particular, Hoffman proved this lower bound of the chromatic number, and Wilf proved this upper bound. And the last kind of the significant result that I really want to talk about here is the following, which says that if G is a graph with maximum degree delta and average degree bar D, then its largest eigenvalue is sandwiched between these two things here. In particular, if G is a D regular graph, its mu1 is going to be exactly D. So it's maximum degree and its average degree are the same. Okay, so we'll prove this. First, the lower bound uses the following basic factor from linear algebra. If you have a real symmetric matrix, then its largest eigenvalue is equal to this expression here. This is known as like the Rayleigh quotient or Grant-Fisher, whatever you call this. And in particular, this term is lower bounded if we take x to be the all ones vector, or any particular vector that you like. But if we take the all ones vector, you can rewrite this expression as the sum of the degrees of your vertices divided by the number of vertices. And that's just the definition of the average degree. This is that. And kind of the more important direction I want to prove is this maximum degree upper bounds, the largest. And we'll prove this in a fairly spectral way. So we'll let x be some eigenvector of A corresponding to this eigenvalue, and we'll let V be the largest coordinate of x in absolute value. So now we're just going to say some trivial statements. So without the absolute values here, the vth entry of AX is exactly the vth entry of x times mu1. That's just what it means for x to be an eigenvector with this eigenvalue. Again, saying nothing. If we drop the absolute values, this term here is exactly the sum over all the AUV times XU terms. And we can restrict ourselves to U that are adjacent to V because every other term is going to be 0, just by how the adjacency matrix is defined. And now we're going to apply the triangle inequality here just to bring in the absolute values. And now these AUVs are all going to be equal to 1. And this XU term is going to be at most xv in absolute value, just by how we chose v. And so each term here is going to be at most xv. And the number of terms here is exactly the degree of the vertex v. Now the degree of v is at most the maximum degree. So we get this thing here is most this thing here. And that just says that the absolute value of this largest eigenvalue is at most the maximum degree, which implies this result. Any questions about this proof or anything else? Okay, cool. So now we can actually generalize this proof a little bit. Namely, the same proof applies if we don't consider the adjacency matrix, but some kind of pseudo adjacency matrix. Namely, if we look at some matrix M, which is Hermitian, and such that if two vertices are adjacent, then the UVth entry of M is equal to 1 in absolute value. And if it's equal to 0 otherwise, then the largest eigenvalue of this matrix M is at most maximum degree of the graph. So again, the adjacency matrix is the canonical thing satisfying these conditions, because AUV is just literally equal to 1, and it's equal to 0 otherwise. And the point is, these are the only properties of the matrix that we actually use in that proof I just sketched out. In particular, kind of the only interesting thing is that here, instead of using that AUV is equal to 1 to get to this part here, we use that its absolute value is now at most 1. So, okay, this is a generalization, but I don't really like generalization for generalization's sake. But fortunately, that's not what this is. This is actually genuinely a useful observation in something that I'll prove for you in a moment, namely how Huang's proof of something called the sensitivity conjecture. This was proven, I think, early 2019, so fairly recent, and it solved this outstanding problem in computer science using almost just basic linear algebra, basically, and this observation.
Wait.
Yes.
You just said that this proof technique was in 2019?
Yes.
Oh, that is amazing. That brings me great joy.
Yeah, no, it's so this problem. Yeah, I'll address it a bit more, but there was a 30-year-old problem in computer science that people cared about a lot, and
yes.
yeah, elementary linear algebra solved this problem.
What's the problem?
Great question. So to state the problem, we're going to first define the n-dimensional hypercube. So this is, for example, the 2-dimensional hypercube is just square. The 3-dimensional hypercube is the cube, and it goes on and on. A bit more formal definition is that you can recursively define its adjacency matrix by taking 2 copies of the previous dimensional one and then putting the addition matrix. And combinatorially, what this is saying is that for example, to build a 3-dimensional cube, I take a 2-dimensional cube and then another 2-dimensional cube, and then I add an edges matching up the corresponding vertices. That's combinatorially what's going on here, but you can just accept that this is the definition of the adjacency matrix. And then the other definition I need to state is an induced subgraph. So an induced subgraph of the graph G is a subgraph you get by taking some subset of its vertices and then including all the edges that involve 2 vertices of this subset. So a picture is worth 1,000 words. So if we start with this graph here, the 2-dimensional cube, then one induced subgraph is to take all the vertices, in which case we also take all the edges, which gives back the original graph. Yeah, so induced subgraphs. So let's look at the example of the 2-dimensional cube. So for example, if we keep all 4 vertices of the cube, then we also have to keep all the edges, and we just get back the original graph here. If instead we choose the induced subgraph on these 3 vertices, then we keep these 2 edges and delete this vertex and all the edges involving. Similarly, if we take to the opposite vertices, we'll just get this empty graph on 2 vertices. If we choose these 2 vertices, we get an edge as an induced subgraph. Choose one vertex, we get one vertex, and we choose no vertices, we get the completely empty graph. So these are all of the isomorphism, the induced subgraphs of the 2-dimensional. And now with these results stated, I can, or definitions established, I can state this result of Chung, Ferretti, Graham, and Sewar, which says that if you take H to be some induced subgraph of the n-dimensional hypercube on one more than half the vertices, then this induced subgraph has maximum degree at least this quantity here. So concretely, For the two-dimensional cube, this says if we take an induced subgraph on 3 vertices, then this induced subgraph will have maximum degree at least a half. In fact, it has maximum degree 2 in this case, but the lower bound just says that. And a couple comments regarding this. The first is that it's important that we look at half the vertices plus 1, or at least that much. If we only look at half the vertices, then like in this example here, we can always choose our vertices in a careful way so that the graph induces no edges. And in particular, we can't say anything trivial about its maximum degree. And the other thing that you might notice is that at least for n equals 2, this bound is not sharp. The true answer is 2, but this is only saying half. You might ask, can you improve this? Maybe a naive guess is that you can always get a lower bound of n for the n-dimensional hypercube. That's what's true here. But that's actually not true because they also proved that there's a careful way of choosing an induced subgraph so its maximum degree is only square root of n. So in other words, it may be true that you can boost this bound up, but you definitely can't do stronger than square root of n because there's examples showing that you can't do better than this for the maximum degree. This is a fine, combinatorial question that you might like if you like combinatorics. But even if you don't, Gaussman and Lineal showed that this problem is actually equivalent to some problem in computer science that I won't go into the details about. But the point is that, roughly speaking, they show that if the square root of n is closer to the true answer for this problem, then some big problem, some conjecture called the sensitivity conjecture is true. And if the log n answer is closer to the truth, then it's false. So this purely combinatorial problem is equivalent to some how sensitive Boolean functions can be. Words. And the remarkable result of Huang showed that the square root of n answer is basically correct. Showed that if you take more than half the vertices, the induced subgraph is going to have maximum degree at least square root of n. So this example they did is basically right on. And as I noted earlier, this problem has been open for about 30 years between when it was stated and Huang, and it was proved, and it had important consequences. People cared about it a lot, and the proof just used basic linear algebra, which I'll go through the next 5 minutes for all of you. So yeah, the key, unless Baki has something silly to say.
I do. I mean, it seems like Huang literally not only proved the sensitivity conjecture, but also proved the theorem that you can never know too much linear algebra. Decidedly.
Yes. Yeah, really, yeah. Yeah, and it wasn't even like, as we'll see, it's not even like difficult, like, oh, this like super obscure like linear algebra. It's like just the Cauchy interlacing theorem. That's the only like result you actually need to prove this. And the key observation is the setup. And the setup for Huang is that you don't want to look at the adjacency matrix of the hypercube. You want to look at the twisted adjacency matrix. So this is defined recursively as follows. So it's almost the exact same definition as the adjacency matrix, but you add in this minus sign here. That's the only change you make. So it's just going to be the adjacency matrix of the hypercube, but now with like half of the ones now minus ones. That's the setup. All right. And a basic lemma is that the eigenvalues of the matrix are plus and minus square root of n, each occurring with the same multiplicity. And to prove this, we prove by induction that the square of this matrix is exactly n times the identity matrix. The base case is trivial. For the inductive hypothesis, we just use this recurrence relation to show that b squared is literally this expression here. And now inductively, we know what b squared, the n minus first one of this is just n minus 1 times the identity matrix. So if you work out this algebra, you get n times the identity matrix. And because b squared equals n times the identity matrix, all its eigenvalues are going to be plus or minus square root of n. Moreover, its trace is 0, which basically means that each of these has to appear with equal multiplicity. So maybe I went through this a little fast, but I assure you these computations are just basic routine, very elementary stuff. And the other fairly elementary results we need is the Cauchy interlacing theorem, which says if you have a big matrix B, which is n by n, and if you look at some principal submatrix C, which is now m by n, and if you happen to know the eigenvalues of B are this, then the eigenvalues of C are going to be sandwiched between these two eigenvalues of your bigger matrix B in this fashion. And the exact numbers don't matter too much, just that they work out. And the last result we need is just this thing that I stated near the beginning of the talk, which is if you have something that looks like an adjacency matrix, then its largest eigenvalue is going to be at most the maximum degree of the graph we're looking at, right? And literally these two lemmas and this one here are all we need, and now we can prove the sensitivity. All right. So to do this, once again, recap what we're trying to do. The enemy is going to pick half the vertices plus 1 vertices from the hypercube, and then form some induced subgraph on this vertex. So perhaps a natural thing to do is to look at, given the setup, is to look at the principal submatrix, which we take the twisted adjacency matrix, and then look at the induced subgraph or the induced submatrix defined using the rows and columns induced by the vertex set of the induced graph. Okay. Now by Cauchy interlacing, the largest eigenvalue of this matrix C is going to be at least the 2 to the n minus first largest eigenvalue of B, and the first 2 to the n minus 1 eigenvalues of B are all square root of n. So this just barely works out. If we were looking at a slightly smaller matrix, this would go to the 2n minus 1 minus 1 eigenvalue. This would be minus square root of n, and we wouldn't be able to say anything. So this just barely computationally works out. And the other fact is that this C is, a pseudo adjacency matrix. It satisfies the hypothesis of this theorem here. So the maximum degree of the induced subgraph H is going to be at least the size of the largest eigenvalue of C, and well, by this thing above, that's at least square root of n. So that proves the sensitivity conjecture for you, all on one slide using 3 basic lemmas. Yeah, any questions about this almost embarrassingly simple proof?
This is one of the best mathematical stories I've heard in a long time.
No, it's great. Like I love this. This is one of my favorite theorems. In addition, partially because of how stupid it is in some sense. Like, it's beautiful, but also stupid.
Do you know what journal this paper is published in, and if it's like 2 pages?
I don't know. No, I think it is like 8 pages. And I'm like, you certainly could shorten this, but like include.
Yeah,
like,
sure. He just brags for
Yeah, I want to say it might be in Annals. Someone should fact check me though. I don't actually.
Okay, I'll look it up. I was just wondering, like, how when you're going about deciding when you have a trivial proof of an epic conjecture, like, does it go in an epic journal? That's really, really great. I love it so much.
Yeah, and I guess you could also say that this proof is, like, depending on your perspective, really highlights either the beauty or the annoyance of combinatorics with its, very clever and slick proofs that, no one can find for 30 years. But yeah, so this is the spectral, the sensitivity conjecture. Now that I've talked about how great the spectral graph theory is, now I want to talk to you about why it sucks sometimes, or at the very least why it has some limitations. And in particular, the example or the reason it has limitations is because of these 2 graphs here. You can go home and check that both of these have the same spectrum for their adjacency matrix. Both of them are this multiset here. And whenever we have 2 graphs with the same spectrum, we call them co-spectral. And the problem with these 2 things is that this immediately implies the following result, is that it's impossible to determine from the eigenvalues of A whether or not the graph G is connected or not. And the reason is the enemy could give you this multi-set of eigenvalues here, and you wouldn't know whether they're talking about this picture here or this picture here. So just from these eigenvalues, you could not say with certainty whether the graph is connected or not. Similarly, you can't say whether the graph contains a 4 cycle or not, whether it contains a vertex of degree 4 or not, and so on and so forth. So any examples where you have 2 non-isomorphic graphs with the same spectrum, that's going to be some limitation for the adjacency matrix to state it. But partially motivated perhaps by the sensitivity conjecture, we know that it's not. You shouldn't always look at the adjacency matrix. This twisted adjacency matrix, for example, was some other graph matrix that we could look at, and that helped us solve the specific problem that we were looking at. And more generally, we have at our liberty to choose any kind of matrix we want, and then try and argue things about that. And perhaps in the broadest terms, spectral graph theory is the following four-step process. We first start with a graph G. We then define some matrix in terms of this graph. We then compute its spectrum. And then somehow from the spectrum, we determine combinatorial properties of our original graph. So this process is, in some sense, really what spectral graph theory is all about. Often, this MG is going to be the adjacency matrix, but also often it's going to be something completely different. And I'll note that in principle, you can use this method to solve any problem, but in practice, that's not always going to be the case. So for example, we could define the matrix xg to be the matrix which is the chromatic number of the graph G times the identity matrix. And if you give me the spectrum of this graph, of this matrix, I can tell you exactly what the chromatic number of a graph G is, because it's literally just that eigenvalue. So this step is great. And in some sense, this step is also great because once I have this matrix, I can tell you what it is. But like there's actually computing this matrix is an NP hard problem. So even though in principle this matrix is great, it's in practice not feasible to work with. So it's not necessarily obvious in general how to find a matrix that does all these three steps successfully. But fortunately, there is like a wide theory about certain matrices that work. So we've already seen the adjacency matrix and some properties you can get from that. In the last couple of minutes, I'll talk about two of the other most popular ones. The first being the combinatorial laplacian matrix. To define this, I first want to define the D to be the diagonal matrix, whose U entry is the uth degree, or the degree of vertex U. And then we'll make the weird definition that L, the Laplacian, is D minus the adjacency matrix. So just as a concrete example, if this is our graph here, then our diagonal entries are going to be the degrees of each of these vertices. So example 4 for vertex 1 and 1 for everything else. And then basically anytime we see an edge, instead of putting a 1 like for the adjacency matrix, we now put a minus, and we put zeros everywhere. This is a definition of Laplacian. And if you're like me, you might ask yourself, why the heck would you make this weird definition? And I still don't have a great answer for that, other than it works out in the end. But here are some words that you may not know or understand that may help. So first of all, you can view a graph as a one-dimensional simplicial complex. And a simplicial complex has boundaries and co-boundaries operators once you assign some basically arbitrary orientation of its edges. And if you apply the boundary co-boundary operator, this is basically what you end up getting, or maybe the co-boundary boundary operator, whichever words make it so that you have a map from vertices to vertices. If you do that, you'll get a matrix, and this is the Laplacian is exactly the matrix that you end up getting. Some other words I can throw out are the abelian sand pile model, or the chip firing model. So this is basically each vertex has some number of dollars or chips, and you fire a vertex, meaning you distribute one chip to each of its neighbors. So for example, if I fire this vertex here, I give away 4 chips, and each of its neighbors gets 1 chip. And that's kind of what this row is representing. And similarly, if I fire this chip, it gives away 1 chip, and the vertex that gets it is this one. So the rows, in some sense, encode moves you can make during the chip firing game or the abelian sand pile. Again, if these words mean nothing to you, that's fine. We're just going to accept that this is the definition. And one of the most famous results involving the combinatorial Laplacian is the following. If G is a graph, then the number of spanning trees, those subgraphs of G which are connected trees, is exactly the product of these eigenvalues divided by n. And in particular, if we look at the complete graph on n vertices, it's not too hard to work out that its Laplacian spectrum is this. And just applying this result says that the number of spanning trees of the complete graph is n to the n minus 2. And another way of stating this result is that the number of labeled trees on n vertices is n to the n minus 2. So that's just because you look at a labeled tree on n vertices, that is just a spanning tree of the complete graph on n vertices, and vice versa. So there are also more combinatorial ways to prove this result. But I really just like this theorem because, it's a completely linear algebraic proof of this, purely combinatorial statement. And it really applies not just to complete graph, but to any graph you possibly can cook up. This is a relatively computationally cheap way to determine what this number of signatures are, in case that's something you care about. Okay, so this is kind of the Laplacian. And the last thing I want to talk about is something called the normalized Laplacian. So what you do is you just take the Laplacian and then you scale it down by the left, on the left and right by this diagonal matrix degrees raised to the -1/2 power. And if you expand out what the definition of L is as D minus A, you can also rewrite this as the identity matrix minus this thing here. So again, concretely, an example here is this thing here has this normalized Laplacian. The point is, for example, you take the combinatorial Laplacian that we had before, and because this vertex here has degree 4, we're gonna 4 to the -1/2 power is 1/2. So that means we're gonna scale down the first row and the first column by 1/2. Because everything else has degree 1, and 1 to the -1/2 is 1, we scale down each row and column by 1/2. And that's just basically what we get here. And the best motivation I have for this definition is from random walks. So a random walk is as defined as follows: you start at some vertex, and then at each stage you uniformly random pick one of your neighbors, and then go there, and then go somewhere else, and then go somewhere else, and so on and so forth. There's a fairly natural model to put on the graph. And the probability transition matrix for this Markov chain you can work out is just the adjacency matrix times the degree matrix to the -1st power. This is just relatively simple state. And this matrix is similar to this matrix here, which you get by multiplying by t to the -1/2 on the left and t to the 1/2 on the right. So now we see the symmetric matrix, so it has real eigenvalues. And moreover, it's basically the same as this matrix here. It's just off by some linear combination here. So in other words, the normalized Laplacian has eigenvalues which correspond to the eigenvalues of your probability transition matrix. And if you're familiar with the theory of Markov chains, that basically says that if you know the eigenvalues of the normalized Laplacian matrix, you also have good control over how quickly random walks converge in this setting. And the only reason we look at, say, this thing here instead of literally just this guy here is that you get a slightly nicer to work with Rayleigh quotient. So the analysis is slightly similar. And there's much more you can say with the normalized Laplacian. For example, it also gives you good control over how few edges you need to cut in order to split a graph into 2 disconnected components. And computer scientists care about this a lot. But for the moment, I'll end things here.
All right, let's thank the speaker. Does anyone have any questions?
I have a question about the stuff, Sam.
Yes.
So far, everything is undirected, and I don't know if you had any edges that had negative values. Is there some extensions to those cases?
Yeah, no, it's a good question. Yeah, so everything I did here, you can extend to weighted graphs. So let's put directed to its side for a second. Yeah, you can I go all the way to the start. Yeah, so if instead of looking at the adjacency matrix, which you put a 1 for each edge, you could instead consider a weighted graph where you have this edge is weighted 7, and instead of putting a 1 here, you'll put a 7. Right? And you have to tweak definitions a bit. For example, you have to figure out what exactly it means to be a walk in a weighted graph, or how many. But there's reasonable definitions you can make for these, and everything I said here carries over to weighted graphs as soon as you make the correct definition. So that's for weighted graphs. For directed graphs, things get fucked up, to put things bluntly. And the reason is this assumption here. You can make a directed, the most natural way to make the, for example, adjacency matrix is that you put a 1 if u points to v, and that's no longer going to be a symmetric matrix is the problem. And because we're no longer a symmetric matrix, you may not have real eigenvalues. So particularly you can't order them in this nice way and say things about the top eigenvalue. There do exist, but also we have the luxury of choosing a different matrix. You might want to there exists other definitions such as like if u points to v, we'll put a 1, and if v points to u, we'll put a -1. So now it's going to be an anti-symmetric matrix, and now it has like all complex eigenvalues. So there exist things you can do for directed graphs. As far as I know, they're not very useful theories. Like for adjacency matrix, there's a lot we can like combinatorially say that's like actually useful for solving problems. As far as I know, there's not too much you can say for directed graph. But maybe there is some nice notion there. So yeah, hopefully that rambling answers your question.
That did.
I think at least you can say the same thing about the walks.
Yes.
That should still, yeah.
Yes, that's correct. So yeah, some results do still carry over, but you can't, for example, well, I guess yes, you can still say the thing for the walk, even these like some of the closed walk should still be this. Is that correct? Yeah, so I think a lot of the walk stuff. So some stuff still does carry over, sure.
Okay.
But a lot of the theory breaks down.
Yeah.
Okay. I had it. So all of these, like the adjacency matrix and all of the matrices that we looked at so far, they're matrices sort of defined on the vertices that are there also matrices that are defined on, like if you have like n vertices, then you can have like however many possible paths or edges that you can have, right? And then that would be like a humongous matrix. Are there things that relate to matrices that are defined on the edges?
Yeah, that's a good question. Yeah. So I think the short answer is yes. I mean, certainly you can make definitions that involve these, and in particular, people have attempted to make spectral theories for hypergraphs. Again, with there are technically results that are true, but they're not super useful. And some of these, I think, rely in particular on these sorts of definitions where you look at the edges instead of the vertices. And yeah, so I would say the short answer is like yes, but I don't know to what extent they're actually useful in practice, or at least of what's known. But yeah,
Cool.
yeah.
Any other questions? Okay, I actually have two questions. One, do the singular values of the adjacency matrix tell you anything?
Yeah, so again, for everything I've talked about up to this point, it doesn't matter. I mean, yeah, the answer is yes, because the singular values are equivalent basically to the eigenvalues. But for some of these theories, for example, like the directed graph case, where you don't have a symmetric matrix, there have been attempts at
yeah, okay, that was where I was going.
trying to do something. So yeah, again, the short answer is, as far as I know, not too much. Actually, no, there is some computer science problem called the k-means problem, where you have like point sets and you want to split them into like k sets so that they're like equidistributed, and like here you end up defining a matrix which is not symmetric, and there the singular values are important for how good this algorithm is or how effective this distribution is.
Sweet.
That's kind of a tangential thing, but yeah. So yeah, to some extent, yes.
My second question is, I'm not even exactly sure how to ask this, but can you build and use adjacency matrices for infinite graphs? Like, can you use analysis? And I don't know, you'd have to assume a lot about your graph probably, but.
Right. Yeah. So yeah, that's a good question. So again, the answer I think is to some extent yes. So there's something like people have considered like the infinite d-regular tree, which it's just it starts anywhere and just goes d, and like you can morally, I don't know to what extent about the rigorous like analysis or whatever, but like people can like morally say like, morally it's like largest eigenvalue. Well, its largest eigenvalue is d because it's a d-regular graph. But you can also say like the second largest eigenvalue should be like 2 square root of d, I think, and like in some sense this is the best expander graph. I don't know if this word means anything.
Yeah, it does. Yeah.
But yeah, so people like you can say that the d-area tree is the best d-regular expander graph in terms of its spectral graph. And this you can use this to like imply things about finite graphs, basically by making a reduction from the d-area tree to here. I don't know the exact details of this, and I don't know to what I don't study too many infinite graphs, but I think to some extent you can say things, but like you said, there are definitely technical complications that have to be
Sure. Cool. All right. Thanks. Any other questions or comments?
Vaki, I thought you would like appreciate this comment, but when you said about infinite graphs, I don't know if you were meaning like if you have some type of manifold, you get finer and finer meshes of like, and like you could take like limits to actually get like a manifold that might be like compact or whatnot. But the Laplacian, the eigenvectors of it, they approach the eigenfunctions of the Laplacian on the manifold, and
Yeah, that makes sense. Somebody's told me this before. That's good stuff. But
yeah, I know
so,
Andreas likes that result a lot.
Yeah, he does. Oh, I forgot. There was another thing about infinite graphs that I have since forgotten. All right, any other questions or comments? More comments about manifolds would be very accepted. All right, fantastic. Let us thank the speaker once again.